Now there is another way of looking at Euclid's algorithm. I can also write this equation. I can also take this equation ahead and write that GCD of A comma B is equal to GCD of A plus BK comma B, where K is any integer. So I can also write GCD of two numbers A and B as the GCD of first number plus K times, or plus or minus K times the second number comma the second number. Why can I do that? I can do that. We have observed from previous examples that if even if I add the second, let's say I have two numbers A and B, and if I add the second number K times to the first number and take the GCD with the second number, the set of common factors does not suffer a change. So since there is no change in the common factors, even if I add or subtract any of the one elements from the other elements any number of times, that's why we can write this equation as well. And we'll see how we can utilize, use this equation as a very powerful tool to solve some very complex questions. I'll take an example that elucidates and clarifies your concept on this. So let's do that problem. Let me make some space. Let's say we have a question that asks us to find maximum of max of GCD of, let's say, n square plus 11 comma n plus 1 whole square plus 11. This is what we are intending to find. Now, or let's say, let me take a general case wherein I can replace 11 with A and get a general result, and probably later on we can put the value of 11 and see. So for now, let's park this max. We'll take this later on. Let's only concentrate on the GCD part, finding the GCD. So if you recall the Euclid's algorithm, let's follow that. I have a smaller number and a bigger number. So in my first step, I'm going to write the smaller number. I'm keeping that intact, and I'm subtracting the smaller number from the bigger number. So this subtraction will give me 2n plus 1. Now this number is a square and this number is linear. So this is more complex. This square is more complex, and my idea of using this algorithm is to go into simpler and simpler kind of a process. So let's try and get rid of this n square thing. So if you remember, in my last development of the algorithm, I said that if I have GCD of A comma B, I can write it as GCD of A plus KB comma B, so for any integer k. So let's apply that funda here and try and get rid of this n square plus A. And so in that case, let me multiply this with the first term with 2 by, or let me do one thing. Let me multiply this term by n by 2 and subtract these two, first and the term that I get by multiplying n by 2 to the second term. So if I subtract it now, and I'm replacing it instead of the first term, so n square minus n square is 0, a minus n by 2. So effectively I'm getting a minus n by 2 comma 2n plus 1. So now I've gotten rid of this square term. Now I have two linears in n, and this makes me think that in a subsequent step probably I can get rid of n from one of these, probably this term, and I can get a constant in terms of a. So in order to get there, what should I do? I need to make the coefficients of n same with opposite signs in both these terms. So if I multiply the first term by 4, I have GCD of 4a. This becomes minus 2n, and if I add these, minus 2n plus 2n cancelled, and I have plus 1, and this is 2n plus 1. I can keep this intact. Now see, here we reach a position wherein I have one term as a constant in terms of a, and the other term is a variable in terms of n. So now this term is an odd, because any odd number can be expressed as 2k in the form 2k plus 1, and so is the first term. Both of these terms are odds. Now let me take a specific case. Let me, if this a were equal to 11, this will actually help you relate to this problem and understand this better. If let's say a is 11, I am finding out GCD of 4 into 11 plus 1, 45, comma 2n plus 1, or in other words, I'm trying to say what is the GCD of 45 with any odd number. 2n plus 1 can be any odd number starting 1. So GCD, if I say that GCD of 45 with 1 is 1, I can as well say that GCD of 45 with 3 is 3, GCD of 45 with 5 is 5, GCD of 45 with 7 is 1, because 45 and 7 are co-primes or relatively primes to each other. Now essentially what we are doing is trying to find out what is this giving me is all the odd factors or divisors of 45. That's what we are going to get, because GCD of any odd number with 45 must have a factor of 45. 7 was not the factor of 45. So I am only considering in odd numbers, and I am only considering the factors of 45. So I must have odd factors of 45. This is what conclusion I get from here. So that's very important. So my next odd factor is 9. Then I have a 15, and the largest odd factor is 45. So this is a set of values which could be the answer to this GCD of 45, 2n plus 1. However, now let's get back and substitute a max from here. If I were to say what's the max GCD of 45, 2n plus 1, I put a max over here. So among all these possible values, what's the max value? It's 45. So 45 will be the max GCD. Now let's get back to this question and generalize. Similarly, if I was to find the max GCD of this, then what that would be? It will be all of the odd factors of normal GCD of 4a plus 1, first of all, with 2n plus 1 will be all the odd factors of 4a plus 1 till the number itself. So what will be my max GCD? It will be equal to 4a plus 1 itself. So I hope you understood how we went about solving this question, and in each subsequent intermediate steps how we utilize the algorithm that we studied before this. So this should clear your doubts on applying Euclid's algorithm. Now let's talk about an extended version of the Euclid's algo, which is also sometimes known as Bezout's identity. So let me make some space. So let's talk about extended Euclid's algo, or also known as Bezout's identity. So what does it say? For any two whole numbers, for any two whole numbers A and B, there exist integers x and y. There exists integer x and y such that GCD of a comma b is ax plus by, right? So for any two whole numbers a and b, there always exist integers x and y such that GCD of a and b is the same as, ax plus by. In other words, I am trying to say that GCD of a and b is a linear combination of a and b. So I am also trying to say that this GCD of a and b is the linear combination of a and b, and that's what I can see here. This is a linear combination, right? So if that is the case, let's understand that in a particular case wherein two numbers are relatively prime, that means that the GCD of the two numbers is 1. So let's say if two numbers are relatively prime or co-prime, so GCD of those two numbers is 1. I can always find two integers, let's say r and s, such that ar plus bs is equal to 1. That's what I can get from this algo. This is what I can derive from this algo. This is a specific case when these two numbers are relatively prime. So in that case, I can always find two integers r and s such that two or even more integers perhaps, but there will be multiple integers that integer values of r and s that would satisfy this equation. However, for the sake of simplicity, we generally consider the smallest values for the purposes of solving our questions. So ar plus bs will be equal to 1, and I can always find those r's and s's. Let's take an example. I know that GCD of 4 and 9 is 1 and they are relatively prime, so I can always find two integers or more integers r and s such that 4r plus 9s is equal to 1. For example, if I took r is equal to -2 and s is equal to 1, so this becomes -8 and this becomes +9, so this satisfies the equation. There will be more values of r's and s's which would satisfy this equation, but let's take the case of the simplest values of r and s. So ideally, why I am trying to discuss this here, specific example here, is because this has got some application, and a very good application for that matter. Why? What is it applied in? This particular set of information forms the basis for Chinese remainder theorem. If there are two relatively prime numbers, I can always find at least two other integers such that ar plus bs is equal to 1, and this forms the basis of Chinese remainder theorem. This theorem is something that we can take up in the later videos and try to see where and when do we apply Chinese remainder theorem. So now we are almost we have understood the concept of Euclid's algorithm and the extended Euclid's algorithm. We can take up some other interesting videos in the next session.